Welcome to the Explainer. Today, we're going to explore that invisible world. The one that lives right between the marks on a ruler. Our journey's going to start with a simple broken toy, but believe me, it ends with a tool that can measure the entire universe.
All right, let's dive right in with a simple story. This is Sonu, and he's just watching his mom try to fix his toy. But she's hit a snag, and the reason why is, well, it's actually pretty profound. It all comes down to a tiny, almost imperceptible difference. You see, his mother has a couple of screws, and they look identical. She tries one, nope, it just won't work. She tries the other, and it fits perfectly. Now, to Sonu, they look exactly the same, but that tiny difference in length, it's everything. Now check this out. When Sonu puts the screws against a basic ruler, one with just the whole centimeter marks, he can't see any difference. Both screws just look like they're almost 3 centimeters. And this is the whole point. The tool he's using is limiting what he can actually see and understand. This leads us to a really fantastic question. If your eyes can't see a difference and your tools can't see it either, how do you measure it? How do you even give a name to that tiny, invisible space that makes one screw fit and the other one fail? The answer is so elegant in its simplicity. We just have to zoom in. We need to invent smaller units of measurement by dividing up that space between the numbers we can already see. And we call these new units tenths. You just take that gap between, say, 0 and 1, or between 2 and 3, and you slice it into 10 perfectly equal parts. Each one of those little slices is now a tenth of a whole centimeter. And boom, this shows the power of the idea perfectly. With a more precise ruler that actually shows these tenths, Sonu can finally see the truth. The screw isn't just almost 3 centimeters. It is exactly 2 whole centimeters plus 7 of those new tiny tenths of the next centimeter. And we have a really clear way to write this down and talk about it. We can write it as a mixed fraction, 2 and 7 over 10, and we say it out loud as 2 and 7/10 centimeters. It's like we've created a new language, a language for precision. And what's really powerful here is that working with these new numbers isn't complicated at all. If you want to add 2 measurements like this, you just do it in pieces. First add the whole units, then add the tenths. It's just a simple extension of the math we already know. But just when you think tenths have solved all our problems, a new challenge always seems to pop up. What happens when you need to be even more precise? Our source gives us this great example. Imagine taking a sheet of paper and folding it exactly in half. When you measure the new folded length, you find that the edge lands right between the tenth marks on your fancy ruler. So we're stuck again. So we're facing the exact same problem as before, just on a much smaller scale. We're trying to measure a space that our current tools just can't define. So what do you think? What's the next logical step? Well, we do exactly what worked the first time. We divide by 10 again. We take each of those tiny 1/10 spaces and we slice them into 10 even smaller, more precise parts. These new slivers are called hundredths because, it now takes 100 of them to make one whole unit. And with this incredible new level of precision, we can finally give that folded paper an exact measurement. It's 4 whole units, 4 of our tenths, and 5 of our brand new hundredths. Perfect accuracy. Okay, this is the moment where we zoom out. We've been busy solving these specific measurement problems, but in doing so, we've stumbled upon this beautiful universal system that was hiding in our numbers all along. But have you ever stopped to wonder why it's always 10? Why tenths, then hundredths, then thousandths? We could divide a unit into 4 parts or 12 parts, so why is the number 10 so special? This chart here reveals an incredible symmetry. On the left side, you've got our familiar whole numbers, ones, tens, hundreds, where each place is 10 times bigger than the one to its right. Now, look at the other side of that little dot. Our new fractions follow the exact same pattern, but in reverse. Each place is 10 times smaller. It's a perfect mirror.
And the reason is, our entire way of thinking about numbers, the system we use for everything from counting our change to calculating cosmic distances, it's all built on the number 10. Using tenths and hundredths isn't some new invention. It's just a natural extension of the system we already had.
This quote really just sums it up perfectly. The pattern is unbroken. As you move from left to right across any number, crossing that decimal point changes absolutely nothing about the rule. Every single step is a simple division by 10. And this elegant system isn't just some abstract math concept. It is the hidden architecture that makes our entire modern world possible.
Think about it for a second. This relentless push for more and more precision, dividing by 10 over and over again. That's what allows engineers to build stable bridges, it's what allows doctors to prescribe the exact dose of medicine, and it's what lets scientists build the microchips that power our lives. It all hinges on being able to accurately measure beyond the whole number.
And this really gets to the big idea here. We started with Sonu needing to find the right screw, and that journey has led us to this one humble dot, the decimal point. It's not just some punctuation in a math problem. It's a gateway into a world of infinite detail, from the size of an atom all the way to the distance to a star.
Which leaves us with a final thought to ponder. This system gives us a window, a way to see and understand the infinitely small. Now that we have this incredible power to measure things we can't physically see, the only question left is, what will we choose to discover with it next?